Hello students, welcome to the next section of set theory part 2 under prerequisites to probability. So in set theory part 1 we have considered or we discussed a few concepts like uh, right, so definition of set, right? So the first one, definition of sets, we discussed what in by the definition actually, and then representation of sets, so how to represent the sets, listing out the elements as set builder form. Similarly, special sets we have discussed versus like empty set, right, which is having no elements, universal set, the biggest set, right? And representation of sets through different pictorial representation, that is Venn diagrams, right? How to represent a set with using different geometrical way. And next one is subsets and proper sets, right? And cardinality of a set. So if you take any set, how many number of elements are there in that set? So based on that, we decide cardinality. Similarly, power set. So this is another set what we discussed. Okay. So these are the few concepts we discussed in part 1. Now let us continue for a few more concepts in part 2. Okay. So now here we are going to discuss about set operations. Just like a number system, right? You know that we apply some operations, right, from lower classes, right? Addition of numbers, subtraction of numbers, multiplication, division, right? The same way on sets also we apply some operations. So the first operation is union of sets, right? This is the union of sets. So what do you mean by union of sets? Suppose I'll take two sets A, B. Okay, for example, A, L, B, I'll take it, and I'll denote A union B like this, A union B. So what is this A union B? So it is containing the elements which belongs to A or which belongs to B. Of course, the elements which are also belongs to A and B. And now if you take this Venn diagram, right, this is the universal set, rectangle, we know that, and this is the set B, this is set A. So here you can see that we can, in A union B, three parts you are able to see. Now, this is actually the area which is belonging to only B. We say only B. This is the area which is belonging to both A and B. And this is the area belonging to only A. So now what I said, A union B means the elements belongs to A, the elements belongs to B, and also the elements belongs to A intersection B. So that means we take all these three areas, first, second, and third. Now these three areas together will give A union B. So that is what A union B. So we can take, for example, here A is equal to 1, 2, 3, 6, B is another set. So A union B means I need to cover the elements which belongs to A or B, okay, and of course belonging to both also. That means, for example, 2 you take 2 and 6 which are belonging to both, that also will take. That means overall we'll consider all the elements, okay, belonging to A as well as belonging to B together, all will list out. So that is A union B. So A union B, generally if you just roughly if you take as a Venn diagram, suppose this is A and this is B, so we'll consider all areas just like lower classes how we have done. So this is the total area covered by A union B, right? This is the area. So the first, second, and third together, these all, right? So this is what A union B, right? Similarly, intersection. And it's very simple to understand. Intersection is nothing but the elements which belongs to both A and B, right? You can see X belongs to A and X belongs to B. Whichever the elements belonging to both A and B is nothing but A intersection B. So now this is the area, right? You can see that this is the area, right? It is the area which is belonging to both A and B. I mean B and A. So this is coming under A intersection B. The elements which belongs to common, right? So that is the one, right? And here you can see that A is a set, B is a set. Now what are the elements which belonging to both A and B means? So one is 2, right? 2 is belonging to both, and 6. 6 is also belonging to both. So that means A intersection B is going to be, right, 2 and 6. So simple one. So you have to concentrate more on this, but this is the area, right? So if you take for example A and this is B, so this is going to be A intersection B, right? So the area which covering in both A and B, right? So that is intersection. And yeah, this is one important proper definition which we use in probability. When do we say two sets are disjoint? right? So disjoint, no joint, right? Disjoint. Okay. So if the two sets are said to be disjoint, okay, if A intersection B is equal to empty, right? A intersection B must be empty. There must not be any common elements. Okay. So maybe this is not the correct diagram. I'll show that. So suppose this is one set B or A, another set is like this. No, they should be like this. So no, actually this is not common. It should not be like this. This is what example is showing. So it should not be like this. There should not be common elements. Okay, these two sets are not disjoint. But here you can check that these two sets are disjoint. Suppose you take some elements here and here also some elements. So A is completely different from B. A is completely disjoint from B. So if any two sets are like this, whose intersection is empty, see, whose intersection is empty, then those two sets are said to be disjoint. And here you can say 1, 1, 2, 3, 6, 4, 7, 8. Now what you can say that these two are disjoint means yes, because A intersection B is equal to empty, because there are no common elements. So empty, disjoint means A intersection B equal to empty, right? So this is one thing you try to recollect. Now, a complement of a set, right? So this is another operation, right? Complement of a set. So when you take A is any set, right? For example, A, I'll take any set. Generally, the complement of A is denoted with, sometimes will denote with bar, A bar, or otherwise A complement, or sometimes A prime. Okay, any notation we can use. So what do you mean by complement? So whenever you discussing about the complement, so we need to refer, or we need to consider universal set also. Now I'll take universal set U. A is any subset of U. You know that universal set is the biggest set, which is consisting all the sets as subsets. So A is any subset of U. Now for this A, what is the complement? Simple. The elements which belongs to universal set but not in A, or but not to A, right? So A complement is a set, right, which is consisting of all the elements of the universal set U, but not in A. That means outside of A. You can easily do. This is inside of A, area A. That is the area belonging to A, and outside of A means this is the one, right? So this is the total area which is belonging. And roughly, if you want to show, say for example, this is the diagram. This is U, and this is A, and outside area. So what is the outside area of A? So this is the area. You can just show the slide, right? So this is the area which is lying outside of A, right? So this is A complement, a complement of A, right? So now, for example, here you can say U equal to 1, 2, 3, 4, 5, 6, A equal to 1, 3, 5. And I want the elements which belongs to U but not to A, right? So you can take the 2 which is belonging to U but not in A. It is again 4 and 6. See, 2, 4, 6 are belonging to universal set but not in A. So they are belonging to A complement, right? So this is one property, right? So A complement is another operation which we apply on a set. Now, set difference, right? So we have just, when you take two sets A comma B, we have applied two operations already. One is what is A union B, another one is what is A intersection B, right? Now I'm applying one more operation, A minus B. Of course, I can write A minus B, I can define A minus B as well as B minus A. Now, what do you mean by A minus B? So this is just like a complement, okay? Just like previous one, complement. For example, just now I told you what is A complement, right? So A complement, right? So that is, I told you that elements belonging to U but not in A. So that is also represented in the form of this one, U minus A. So what do you mean by U minus A? The elements present in universal set but not in A. So remove the elements, okay, which belong into A, right? So those elements, if you remove whatever the leftover elements in U, that is A complement. Now this is the similar way how you define A minus B. So when you take A minus B, so I want the elements of A, but do not belongs to B. Now, for example, you see elements of A, these are the four elements of A, right? These are the four elements of A. But I want those elements of A which belongs to A, of course, which present in A but not in B, right? Which belongs to A but not in B. But you take these two, even though these two are belonging to A, but they are also belonging to B, so we don't consider them, right? We don't consider them. But I want the elements belonging to A but not in B means I will take these two. So this is the part which is A minus B, right? So you can see the definition. X is such that X belongs to A and X does not belongs to B. X belongs to A and not belongs to B. That is A minus B. Similarly, can you guess what is these two elements are referred? And this is nothing but B minus A, right? So elements belonging to B but not in A, right? So all X, right? You can say all X such that X belongs to B and X does not belongs to A, right? This is the one. Or simply we can through Venn diagram I can show like this. Okay, for example, if you check this, say for example, this is one set, this is another set, this is A and this is B, and this is the area which is A minus B. So you can see that this is the area which is purely belonging to A but not in B, because this is also a part of A but also belonging to B. We don't consider this. This is A minus B. And what about this one? This is B minus A. Of course, this is A intersection B. This, we know that. So this is A minus B, this is B minus A, right? You can check that. And here you can see the example 1, 2, 3, 5, 7, 1, 5, 6, 7. I want the elements of A which do not present in B. So 1 you cannot take, 2s I can take. 2 is an element belonging to A but not in B. 3 is an element belonging to A but not in B. Similarly 7. So 2, 3, 7, 2, 3, 7 are the elements belonging to A but not in B. That is A minus B. Similarly, can you tell me what is B minus A? The elements belonging to B but not in A. So 1 present in A, B also, 5 also present in A, I cannot take. 6, yes, 6 is an element belonging to B but not in A. Similarly, 8. So this is B minus A. So I can find out B minus A, A minus B. This is another one. Of course, we can also call it as A minus B, a complement of B with respect to A. So another way of asking. So A minus B is nothing but complement of B with respect to A, right? So this is the set difference. Now, finally, just coming to this cardinality of union, right? So what do you mean by a cardinality? That means how to evaluate the number of elements in the union of two sets, okay? So how to find out that? So modulus of A union B, number of elements in A union B. So there is a formula by the principle of inclusion and exclusion. Number of elements in A, number of elements in B, right? Adding, and then subtract number of elements in A intersection B. We know this, right? Similarly, for three sets, so modulus of A union B union C, the number of elements in A union B union C is equal to mod A plus mod B plus mod C, and minus, right, number of elements in A intersection B minus number of elements in B intersection C. Similarly, subtract in A intersection C, but again add A intersection B intersection C, right? So these are the two, right, principle of inclusion and exclusion, right? These are the two formula comes under principle of inclusion and exclusion. And we can extend this type of formula even not only for 3 sets, even for 4 sets, 5 sets, arbitrarily n sets also, right? And coming to these final properties. So these operations, whatever we discussed, so union, intersection, difference, complement, they satisfy some properties, okay? So first one is commutative law, we say. So A union B, B union A. So operation you apply union, A union B, B union A, both are same. Similarly, you apply the operation on intersection on A union B. So either you can take A intersection B or B intersection A, right? Clearly, both are same. But when you take this A minus B and B minus A, okay, can we say both are equal, right? So, no, right? So, commutative law satisfied by union and intersection, but not by the difference, right? And the associative law, you can see that A union of B union C, it is A union B union C. So if you want to apply union on 3 sets, how you find out? First you find out union on 2 sets B, C, then you join or you go for the union with A. Otherwise, it is same as finding union of A union B first and then take the union with C. Any order you can take. right? Similarly, intersection, and this is distributive. A union of B intersections equal to first A union B, see, A union B intersection A union C. We say union is distributive. Union is distributive over, right, intersection. And the similar way here, union intersection is distributive over union, right? These two. Again, De Morgan laws, A union B whole complement equal to A complement intersection B complement, right? When you take the complement of A union B, it is expanded as A complement intersection B complement. So union will become intersection. Whereas if you take A intersection B whole complement, we can take A complement and intersection will become union B complement, right? So by using Venn diagrams, we can prove all these properties. But for us, but meanwhile, if you remember this and understand the meaning of these properties is okay. And again, finally, complementary laws, right? So we know what do you mean by A complement, right? I told you that A complement is nothing but the elements present in universal set, but not in A. So in place of A, if I try to find out what is the complement of universal set itself, so it is nothing but the elements present in U, but not in U. The elements present in U, but not in U. See, A complement means U minus A. And what is U complement now? U minus U, right? But what is the elements which belongs to U, but not in U? So such type of elements doesn't exist. So obviously it is going to be empty, right? Similarly, pi complement, which is, right, universal set minus pi, right? So all elements of U which do not belongs to empty set. So that means same set U. And we say law of double complement. A complement of complement is A. Similarly, A union A complement. So A is nothing but here inside of A complement is outside of A. And when you join together these two, it is going to be total universal set. And similarly, inside of A, outside of A, what is the common area? Right? This is inside, this is outside completely. And what is the common area means we don't find out any common area because it is quite disjoint, right? So this is empty. So A intersection A complement equal to empty set means we can also say A and A complements are disjoint sets. A complement and A are disjoint sets, right? So these are the few properties of defined on a sets. So try to just recollect that. So these are the few operations which we applied on sets, and with this we can come to the end of the second part. So we have covered total basics of set theory. With these basics, very comfortably we can enter into the probability, right, concept, right? So it will be very easy. So to discuss probability, we require one more, because when you are doing the problems of probability, we also discuss one more concept, which is combinatorics. Okay, in the next session, I'll give a brief description about the combinatorics, and right, so then it will be very easy for you to follow the probability concept, right? So with this, I'll stop this session. I'll end this session here. Okay, thank you all.